we're going to have, let's say, measurements that we're going to make. And those measurements are going to have, a certain amount of uncertainty in it. And what I'm going to do is teach you how to accurately say what that uncertainty is, and then accurately tell you how that certain uncertainty is going to affect any calculations you do with that data. Okay, that's the goal here, and that's what error propagation is all about. There it is. So I'm starting with this picture right here that you've got laying on your document cam, and really what I'm looking at is I just didn't want to write these numbers over again. Okay, in fact, I'm probably going to give you the same notes. I don't know yet, but anyways, I've got these 10 pieces of data, and let's just focus on the first row right now and not even paying attention to that. So that's our data. And what I want you to think about in terms of that is I want you to imagine that we took a really good measuring device, a good centimeter scale, which, by the way, is not this. Okay, but this is really easy to see, and it's got some perks, like the end is not the 0 mark, it's got a 0 mark, and then the end is down here. So where a meter stick or a yardstick often has the 0 at the end, and that's been chewed by some moron kid and kicked and dropped and stuff like that, and it doesn't have that, so it's good. Okay, and it does have a centimeter scale, so that's good as well, only it didn't actually mark the centimeter, so that makes me a little bit mad, right? But I know that a centimeter is about as wide as my pinky nail, so I can tell this was an attempt at centimeters. And sometimes people maybe don't put centimeter on there because they didn't take all the time needed to make sure that this was exactly centimeters. So that's another reason why this is not that good of a measuring device. But you can imagine using something like this, or ideally this would be much better. But in this situation, that steel rule is really hard to read because of the light and the reflectivity of it. But you can see that is a really good one as well. And that's more like what you'd use. Notice the 0 is not at the end. Notice it does say centimeters and that sort of stuff. So I'm going to refer to this one, but I want you to think in terms of that one. And if you wanted to go to the next level, you'd actually use a vernier caliper, which would have an additional scale that allows you to really precisely get that second decimal place instead of estimating it, which is what we do here. So I'm going to tell you that these 10 pieces of data were from measuring the width of some object. Okay, some object that's about 30 some centimeters wide, as you can tell, like 32, 33. So obviously bigger than this thing, bigger than the diagonal across this paper. But we measured it with something like a meter stick. And if you look at a meter stick or this particular measuring device, I think you can see, I'm going to use the pointy end here. The first thing you want to do is look at, when you're using a measuring device, is look how you make a 0. So in this case, you see the 0s there, so that indicates 0. In the case of vernier calipers, you'd see a line that floats back and forth when you roll this thing on your thumb, and then that line runs right into 0 when you close the calipers. So that's what I mean about discovering 0. You got to find out how you make 0. So when you see that, you say, oh, okay, so that line's the thing I measure off of, and that'll help you. In this case, it's just obvious. You're going to line stuff up at 0. If you're using a meter stick that had the actual end of 0, then you want to stay away from that 0 and maybe measure everything from 1 or from 10 or something like that. And just remember to subtract the 1 or 10 or whatever you use. Now, the other thing you got to do is find out what the unit is. And in this case, I told you it's a centimeter, but normally it would be written somewhere, and that would be giving me a great deal of confidence. It does not have it here, so that aggravates me a little bit. But we've established that it's centimeters. So the final thing we need to do is number 3. We need to find out what the gradations are. In other words, how finely marked it is. So we want to take 2 consecutive units, so like 2 and 3 or 1 and 2 or whatever, and we want to start counting the number of spaces between them. So I see right here between the 9 and the 10, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's very rare that you run into something other than 10 or something like that. But lo and behold, right below here, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Wow, crap, right? They went 1/16 of an inch. So that's why I tell you, you always want to check what the gradations are, because what if some jerk made a centimeter scale and put it on 16ths instead of tenths? That would be just hideous. But anyways, so I did count that, and it turns out there's 10 spaces between the 9 and the 10, and the 9 and the 10 are both centimeters, so that's 1 centimeter. And that means 1 centimeter is divided into tenths, and tenth on a decimal place means 1 decimal place. So each of these marks is represented by 0.1 beyond the last one. So you can read it as 9.0, 9.1, 9.2, 9.3, 9.4, and then notice 9.5 is a little taller. That's helpful. That means we don't have to count from 0 every time, right? And then 9.6, 9.7, 9.8, 9.9, and then 10.0. So we know that this thing can definitively give me a measurement that has 1 decimal place. In other words, I cannot mistake a 9.1 for a 9.2. I would have to make a really foolish mistake to do that. This measuring device is completely capable of it. Now, that being said, I can measure, let's say I can measure something and get an error, but I can measure it to, instead of 1 decimal place, let's try measuring something to 2 decimal places. So right here, I'm going to line this up with a 0 really well. That's what I did on the left-hand side. And I'm basically trying to look with one eye so that I look directly over it. And now I see that this is clearly 5.4 something. So because I have that tenth of a decimal place mark, I can definitively say that's 5.4 because it's past the 5.4 and not to the 5.5. Now I look in there very closely, and it appears to me to be just a little bit beyond midway. So I'm going to estimate that to be 5.46. Okay. Now, that could be 5.47, and I wouldn't be able to tell the difference. It could be 5.48, but I'm pretty confident I could tell the difference there. So I would say this thing, since it's a nice flat edge, there's no divots in and out and stuff like that, I think I can measure this to tell the difference between 5.46 and 5.48, or maybe even between 5.45 and 5.47. So I would say this is 5.46 plus or minus 0.01 centimeters. And that is my instrumental uncertainty, okay? If, however, it had maybe an unsquare edge or something weird like that, then I might not be as confident to have an error of 0.01, i.e. an error of 0 or 1 in that last decimal place. If I was doing something, say, like a piece of cardboard or the end of an eraser or something like that, you can notice that this has a rounded edge, which means I got to sort of estimate where that edge is. I could actually take a meter stick or something and mark it off to make sure I get a pretty accurate figure. But even then, that can bring some error in. And if this thing's been worn down, it might not even be square. So this might compel me to say the uncertainty in this one's 0.02. And if it's really bad case, then I might even say 0.04 or something like that. So that's just something you've got to get a feel of, estimating roughly how right or wrong you are. But that always has to be made whenever you're measuring with a measuring device. So meter sticks and centimeter scales like this probably have at least an instrumental error of 0.01. They can't have any smaller than that, because if you're estimating the second decimal place, you got no idea what the third decimal place is, right? If you use a vernier scale, you in principle could estimate between basically the third digit if you wanted to, but what it really does is it gives you the second decimal place with no uncertainty, okay? And it's really complicated to get a third digit out of it. So you would say that is a tough 0.01 uncertainty, meaning you're not likely to call that 0.02, okay? Now with other things like a digital multimeter that measures amperage or voltage, if it gives you 2 decimal places, then you're going to assume the uncertainty is roughly 1 in that last decimal place. And the only reason why you do other than that is either the numbers bouncing back and forth between 5 and 6, 5 and 6, 5 and 6, or the manual says, hey, the uncertainty in this device is 0.02, or the uncertainty in this device is 0.04. Then you call the uncertainty in the device what the manufacturer says. Okay. So that's a little thing about measurement, and you can't get rid of all the error. You're always going to have instrumental error, because even if you took and cut each little space between the 8 and the 8.1, if you cut that into 10 lines and used a microscope to look at it, yeah, you'd get another decimal place. You'd actually be definitively knowing the second decimal place, but be estimating the third. So you got now an error of 0.001 at least, maybe more likely 0.002 or 003. But if you then try to take each one of those and divvy it up, eventually you start to get to the size of molecules and atoms. And when you get on that scale, the molecules and atoms are vibrating, and they're smaller than the wavelength of visible light. So you couldn't see them. You'd have to use something other than visible light to see them. Maybe bombard them with electrons and have a computer tell you what the electron collisions did and told you about where the atoms were. And you'd see this sort of fuzzy edge, and you would still have some uncertainty, not unlike the uncertainty of the edge being all bumpy and gravelly, right? So you're always going to have that uncertainty, and you always got to estimate that instrumental uncertainty first. So if I took a device like this, or a better one, that steel scale, and measured a distance to be 32.91, 33.05, all that good stuff, then I'd want to know, okay, well, what am I going to report as my result? Well, you probably, and actually I should make this a little higher just so you can see. There's a 10th one up there, 32.96. So you might want to get that number too. It's 32.91, 33.05, 32.91, 32.91. I'm trying not to show you the second row yet. 33.05, 32.94, 32.92, 32.96, 33.06, and then 32.96. Okay. So if I wanted to report that data, what I would do is I'm all equally confident in every one of those 10 measurements. So I just add them up and divide by 10, and that would be my estimate of the best value for X. Now, what would I do to put after the plus or minus? You probably all are familiar with the idea of having a value X written as equal to some number, let's say 33.71 plus or minus 0.35 meters. And that's really the way you're supposed to report numbers in science, is you report your most likely value and how much confidence you have in that, or how likely the next person is to get that same result. Okay, that's what this number right here tells. Okay, so you might think the best thing would be now take the standard deviation of these, because you know what's going to happen is basically when you make a plot of data, like a frequency diagram, what you'd make would be a plot of data that would look like this. It would be the number of the values as a plot against the actual value. So in other words, you break it up into 33.1 to 33.19, 33.2 to 33.29, and you'd get a graph that ideally would be like a bell curve, which we call a Gaussian distribution. And the middle of that really is what we call X bar, or X in brackets. And that just means the mean, right? If we're equally confident in all 10 of those measurements, then no one of them is better than the other one. So I just round them up with equal weight and divide it by 10. I add them up with equal weight, divide it by 10, and that's my mean. So that's what would go there. And I said, you might want to say, well, how wide is this type of graph? In other words, what percentage of all the data points fall within some distance of the mean? So you might think, well, what is the average deviation? So that'd be like our first try. We're going to take an average deviation. So we're going to take an average deviation, and the deviation is sigma, which is like xi minus x bar. In other words, that would be x1, x2, x3, x4, x5, on up to x10. And the average, I would compare the difference by subtracting them. So you'd say, okay, well, I'm going to take the average deviation. The average deviation would seem to me to be x1 minus x bar plus x2 minus x bar plus dot, dot, dot on up to x10 minus x bar. And then I divide that by 10 to make the average. And this would work because the x is in centimeters, the x bar is in centimeters, everything would come out in centimeters, which is what I want for my deviation. That would tell me how far away. Well, if you do this process, what you're going to get is x1 plus x2 plus x3 plus dot, dot, dot on up to x10. And then you're going to have 1x bar, 2x bar, 3, 4, 5, 6, 10 x bars. So it'll be minus 10 times x bar. And then, of course, you're going to divide that by 10, which I wrote n before, but 10 is really the number, right? So you now see this fraction right here is x1 plus x2 plus dot, dot, dot on up to x10 over 10. And this one, on the other hand, is 10 x bar over 10. So what is this value? X1 plus x2 plus x3 on up to x10. What's that value?
That's going to be the sum of your x's, right?
Right. So it should be basically the total, and then you divide that by 10. So what's that become? Isn't that just x bar? And 10 x bar over 10 is just x bar 2. So you end up getting 0. So that's why we don't use an average deviation. Now, there's ways you can compensate for that. The problem is you're just as likely to have numbers under the x bar as you are numbers over the x bar. So you'll have just as many negatives as you do positives. So they're all going to add up to give you 0. So your next try might be, let's try the square of the deviation. So let's say the average squared deviation. But of course, there's a problem with that, because if we square the deviations, then we're going to have the units to be centimeters squared. And we want something with the same units as the quantity. So maybe we'll take the square root of the average square deviation. That sounds like a more reasonable choice. So what I'm going to do is I'm going to say xi minus x bar squared. All right, let's say x1 plus x2 minus x bar squared plus x3 minus x bar squared plus dot, dot, dot on up to x10 minus x bar squared. And then ideally, you would want to just divide it by 10 and then take the square root. And that sort of works, but it turns out statistically, that's not a very good thing. In other words, this value gives you a little bit too small of a value to really accurately give you statistics, okay? So it turns out what we really want to do is subtract a 1 from that. So our mean, x bar or x bracket, is given by this fancy formula. The summation from I equals 1 to n, where n is the number of trials, of x sub I, and then I divide that by n. There's also something called the standard deviation, which I'll put equals there. That's going to be s sub x, meaning the standard deviation of x. And with that one, we're going to take a square root, but we're going to take the summation from I equals 1 to n of x sub I minus x bar squared, and divide it not by n, but by n minus 1. And when I do that, that gives me something that's really statistically valid, even for small groups. So in other words, when you're doing 5 data points instead of like 500 or 5,000, this n minus 1 is your friend, okay? And once you start getting to 5,000 versus 5,020, the n minus 1 might as well be n. So it just fixes itself. So that one turns out to be much better. That's the standard deviation. And you might say, well, what does the standard deviation mean? Well, the standard deviation means that, remember those numbers I showed you? So I showed you these numbers, 32.91 and all that stuff. Well, if I were to have done, let's say 100,000 trials instead of just 10, okay? If I had completed, and it could be anybody else too, I'm just saying me because I'm pretending I did the data to begin with. If I had completed 100,000 trials and I found X bar equals, let's say 32.85 centimeters, and S sub X equals 0.05 centimeters, then 68 greater than or approximately equal to 68,100 of them would be between would be between 32.85 minus 0.05 is 32.80, and 32.85 plus 0.05 is 32.90. That's what the standard deviation means. Means if you're going to do 100,000 trials, I expect 68,100 of them to be within one standard deviation of the mean. So we call that X bar plus or minus S sub X. But that's not really the thing that an experimentalist wants to know. Experimentalist has no interest in what its individual trials are going to be. An experimentalist wants to know what its result is going to be. So what if I did this experiment 100,000 times, each of those having this 100,000 trials? What I would really like to know is how many of those separate experiments or what range of numbers would those separate 100,000 experiments have 68,100 of them in. So I really want another iteration. In other words, I want the standard deviation of the mean. This was the standard deviation of the data. I want to do another standard deviation of the means of this. In other words, I'm going to take these 68,100 trials, and now, or excuse me, I'm going to take this 100,000 trials, and I'm going to get 100,000 more of those. And I'm going to take the means of all those 100,000 trials and the means of all these other 100,000 trials and all that. And then I'm going to take the standard deviation of that. That's the number that I want to put after my plus or minus when I try to write a scientific number like, a scientific number like that. That is called the standard deviation of the mean, but it's also called the standard error. And we would call it sigma X. Okay. So yes, if I did 100,000 trials, 68,100 would be between this and this. And in fact, 98,400 would be between 32.75 centimeters and 32.95 centimeters. And in fact, greater than or approximately 99,800 would be between 32.70 centimeters and 33.00 centimeters. Okay, so that's really what the standard deviation brings to you. It brings you 68.1% of the data, whereas the standard error brings you 68,100% of the results. So how do you get it? Well, it turns out if you do the standard deviation of the standard deviation, the equivalent is basically sigma x is equal to, I still got to take a square root. I still got to take the summation from I equals 1 to n of x sub I minus x bar squared. And of course, I took the standard deviation, which was n minus 1. But now that group is going to be big enough that I can actually just take and divide it by n. And that's the actual formula for the standard error. The good news is, once you have the standard deviation, it's super easy. You just take the standard deviation and divide it by the square root of n, the number of trials. Okay. So that's really what we're going to use. We're going to record the best estimate of the data plus or minus the standard error. And that's what we should use. Now, if we find the standard error is smaller than that instrumental error, we did all that calculation for nothing. Okay. We got to throw it out and use the bigger of the two. Always, always, always. No ifs, ands, or buts about it. Always got to use the larger of the two. So statistics can't work you out of the awesomeness or crappiness of your instruments. So if you can only get 2 decimal places, you're not going to get a third by doing that. And what this tells you is if you had an average, say, of 33.96754309. Okay, I added an extra digit in there. 796753009. Anyways, if that was your actual average, and you found that your error, whether it be instrumental error or standard error, if you found that number to be 0.03 centimeters, then what it's saying is, hey, the second decimal place is doubtful. It could be as much as 3 higher or lower than what you wrote. So there's no chance in hell I'm going to know what this digit is. So I would end up recording this as x equals, I use the rounding process. This is 5 or larger. So I'm going to say 33.97 centimeters plus or minus 0.03 centimeters. Notice this digit lines up exactly with where I rounded it off. So you're not going to use sig figs. You're going to find out what your standard error is, and unless it's 0.0014, 0.014, 0.015, 0.016, 0.017, ... In other words, if that first digit's 1, you might wish to keep 2 if it's 4 or larger, no matter how many decimal places there are. So then you'd round it to this place or this place or this place or this place. In other words, in that case, you would write 33.978 or 968 plus or minus 0.015 centimeters. Notice I put the centimeters out there, so I had to put parentheses on it again. So does that make any sense to you folks? Okay, that's really the process. So now let me show you in real life how that works out. So I showed you before, these are some X values that I measured, or I'm pretending I measured. Okay, I did something very specific with it. Okay, those are the 10 values. What if I said, okay, well, actually what happened was I did, let's say 100 trials, and I got this as my mean, and I got this as my standard error. And then one of my coworkers did the same thing and got this as their mean, and this is their standard error, and so on and so forth for each of those. Now the uncertainties are not all the same, so you wouldn't necessarily want to just take the average of all of them. You'd want to use a weighted average And you'd want this idiot group that got an error of 0.12, that's, a bunch of drunk people sitting in the lab, maybe. Okay. Try not to make fun of anybody. So I'll just take a bunch of drunk people. Okay, a bunch of drunk people got an error of 0.12, right? So that one should have a lot less weight than these brilliant people that got an error of 0.01. So how do you do that? Well, there's a different process for means. And if you want to take a weighted average, the weighted mean, so that was the mean up there. Now I'm going to show you how to take a weighted mean. And there's other ways of doing it, but this is probably the most common one that most people use. You'd say the weighted average is always the best estimate. And you would still call it X bar or X bracket, that's fine. But in this case, it's going to be the summation from I equals 1 to n of X sub I over sigma X sub I squared. Okay. So in other words, you're going to take each one of those, errors and square it. And since it's really small, you put it in the bottom, that's going to give the really small ones a lot of weight, and the really big ones like this one, very little weight. And by squaring it, it doubly makes sure that's the case. So I'm going to take that, but now the units become centimeters. The units become centimeters per centimeter squared, and that's just crappy. And not only that, it's got a really unreasonable size, because in fact, the 0.01, the one that had 0.01 uncertainty, that's literally going to be the 33.9 or 32.99 or whatever it was. It was actually 32.91. That's going to be 32.91 times 10,000. So the sizes are all off too by doing that. So you can correct for that by dividing by the summation from I equals 1 to n of the 1 over sigma X sub I squareds. So you can actually square the whole thing and just do that. So that's how you do the weighted average. And notice if all the standard errors are equal, which is like that first case, then this is just going to be 1 anyways. And it's just going to cancel out with that over there. And you'll just get the regular mean formula. So that's what you really do when you have, a bunch of experiments and a bunch of results with a bunch of standard errors. You then take the weighted average. So now that we know that, let's actually look at a real case. So I'm going to open up, show all windows. I'm going to open up this one right here. And this one was actually, I think I screwed up something. So what I'm going to do now is I'm going to take this. I said I'm going to take this and copy it, say Control C. I'm going to add a new sheet. I'm going to put this right here, Control V. And now I'm going to take those columns that I made, the headings at least, and borrow those too. Okay. So what I've done here is I've actually taken the X's that I wrote down on the top of that page. Remember the 32.91 and all that stuff. I've taken all 10 of those and all 10 of those errors, and I'm going to show you how we're going to go about taking the mean. The mean, like I said, I would just take and say, let's say equals the sum of, and now I see that the first number is in C3, so I can type C3, and it doesn't matter if it's uppercase or lowercase. And then I hit colon, and I see the last number is in C12, so I'll say C12, and then I'll close parentheses, and the box shows me whether I did it right. Boom. So that's the sum of all those. So that's the top of that mean. Remember the summation of X sub I from I equals 1 to n? I just did that part. Now for the regular mean, I'm just supposed to take that number and divide it by 10. And you can see, lo and behold, I took C13 and divided it by 10, and I got the mean is 32.967. So that's what our mean is if I'm not taking into account these guys. Now, if I want to take into account these guys, then the sigma squared is going to be in centimeters squared, by the way. So I can go ahead and make that a little larger just to make sure we can read everything. And the reciprocal of that would be 1 over centimeters squared. I think I left off the parentheses. I did. And I can make this wide enough now I can see the units. And the product of the reciprocal and x, that's going to have units of x, which is centimeters, divided by centimeters squared. So that'd be 1 over centimeters. And I'm just trying to be somewhat pedantic on this so we can know exactly what everything is. And this I'll probably leave as a blank like that. So what I'm going to do now is I'm going to compute standard deviation. Okay, so let's ignore this sigma column right now and let's just calculate, say, standard deviation. Well, the standard deviation of this, according to Excel, nope, not that one. So in other words, Excel's standard deviation says this will be equal to equals STD EV. You can see that one works. Estimate standard deviation based on a sample, ignores logical values and text in the sample. This one right here, standard deviation based on a sample from selected database entries. It looks like any of those will do. I'll do the standard deviation one though. And I'll say, I'm going to do the standard deviation of C3, C3 to C12. And that's supposed to be my standard deviation. And did I actually write equals? And I don't know why it's saying a number here.
Maybe it doesn't recognize how you spelled standard dev. Like you have to do it specifically how they want it.
Maybe so maybe I actually didn't write out the way they had. Maybe they had Sandeep. Oh yeah, that's what it was. So I'll just double check STD. Oh yeah, I had two D's in there instead of one. But what does this say? That's the one I ended up using. This function is available for compilability and earlier estimate standard deviation. Yeah, so I guess that's okay. It might not have hurt to use one of the newer ones, the .p or something like that. But anyways, that's that. So the standard deviation of this is evidently 0.6. If I did that myself, what I would want to do is let's add a column here. Actually, let's add a column here. And then another column here. So I'm going to add these columns in here. And the reason why I'm going to do it is I'm going to make a deviation column. Remember, the deviation is x minus x bar. So I'm going to say this is equal to x minus, now the average is this number down here, the 32.967. If I just click on that, it will give me the right number. But when I drag this formula down, it's going to choose this. And when I drag it down again, it's going to choose nothingness. So I got to put dollar symbols in front of them. So I'll put shift dollar, shift dollar. And now it'll always choose C14. So that's my deviation. And that's all my deviations. Now I'm going to do my deviation squared, which should be in centimeters squared. Okay, so now I'm going to take this number and square it. So that's my summation of x sub I minus x bar squared. So now I can take the sum of that, as I did in my table, as you'll see on the sheet. The sum of this doesn't mean anything important. In fact, you would have got 0. But this sum, on the other hand, is equal to the sum of, and instead of typing it, I'm just going to click on the first one and drag it down to the last one, which should give me E3 to E12, and it did. And that's the basically my squares of my deviations summed up. I do not want to take the average of this. So I'm going to do my, just to make sure my formula matches what Excel's doing. I'm going to take this sum here, and I'm going to take the square root of this sum divided by parentheses 10 minus 1, which is just going to be 9, close parentheses. So you see they're exactly the same. And I just figured out what I did wrong in my class this morning. I think I forgot to put the square root. I got a much smaller number for the standard deviation on that one. Okay. So that matches exactly the Excel's version of standard deviation. So I'm happy. And that's what you're going to do in yours. Is I've given you a list of numbers in that worksheet, and you're going to fill it out by hand for those numbers. And then you're going to repeat it with Excel. And well, if you don't have a calculator that does this, and all of yours probably do, then you're going to do it with Excel. But if you do have a calculator, I want you to do it with a calculator. But if you have a calculator that does it, then you can get extra credit by doing the calculator, taking a screenshot of that output, and then do the Excel and turn all of them in. Okay, because I want you to compare all of them and see that they're all on the same page, as I just found that this one is. Okay, now I want to do standard error, and Excel doesn't have that. So I'm going to say standard error. And remember, the standard deviation technically has the same unit, so I can put a centimeters in there, if I could ever type. And the standard error will come out in centimeters as well. For some reason I keep wanting to type a capital. I'm going to make this a little wider so I don't have to lose any units. So for this one, all I have to do is take equals standard deviation, and I'm going to divide it by the square root of 10. Divided by SQRT 10 in parentheses. So that's what my standard error is. Okay, that's the non-weighted average now. Okay, so what this tells me is I should report my value should be reported as X is equal to, notice this decimal place, this is a 019. The uncertainty in the instrument was 01. So I don't need to use the instrumental uncertainty because this is larger than that. But this 9 is a huge fraction of the 1. So that's why I'm going to use 2 digits, and I'm going to round it to the same place as the mean. Okay. So I'm going to say the mean, or the value, is 32.967. And then that's going to be plus or minus 0.019. So that's really what I'm going to, what I report. I just put a plus or minus between them. Okay. I just wanted to show you that on paper. On the actual, let's stop share for a second. So without weighted, I found X was equal to 32.967. Centimeters, plus or minus 0.019 centimeters. And the key thing to notice is this 9 lines up with this 7. Okay. Oh, I'm writing that outside the page. Sorry about that. The key thing to notice is this 9 lines up with this 7. So that's what I got without weighting. Now I'm going to do the part with weighting. We're almost done, don't worry. Go back to sharing the screen. Okay, so now let's take into account the actual weighting. Well, I'm going to take the sigma and I'm going to need to square it. So I'm going to say equals this quantity raised to the 2 power. And then I'm going to copy that down all the way to the 12th row. Okay, so now I've got the centimeters squared. But remember what I needed. I need x sub I times 1 over the error squared. So I'm going to take the reciprocal of this. So I'll say equals 1 divided by that guy. And when you do this, you can see, you can start to make sense of why this weighting works. Remember I told you I was going to take that 32.91 and multiply that by 10,000? Well, there's the 32.91, there's the 10,000. That's what I meant, because the uncertainty would be 1 in 10,000. Now here's the product of the two. That's the sigma, or excuse me, that's the xi over sigma xi squared. So I'm going to say equals this divided by, or excuse me, this times this. Oh, sorry about that. Because remember, I made the reciprocal, so I just multiply it. So it's the product of the reciprocal and the sigma x. So now I just copy this down to row 12 again. And in fact, you can see, look, this 5,146 or this 36,733, those were really some big weights. Now I'm going to take and find the sum. Which comes out in some god awful 1 over centimeters units. That's going to be equal to the sum of these numbers. Okay, so that's the denominator of that weighted average. Or excuse me, no, that's the numerator of that weighted average. Sorry about that. And in fact, I really should have put that right here and said this is the sum and 1 over. And that, ooh, I put it in the wrong place. So that is really the sum of, that's the total numerator is what that is. Now I need to make the denominator, which is the sum of these. So in this case, I'm going to say it's equal to the sum. How did I do it there? Equal to the sum of all these. Okay. So now I can take the standard, or excuse me, the weighted average. That's going to be just the numerator, which is this, divided by the denominator, which is this. And that gives me 32.95. 0364. So let me stop sharing again a second, and I'm going to write the weighted average. Gave me x is equal to 32.950364950364. In case I need them later, I haven't done the standard deviation yet, so I'll put the plus or minus here and leave that for in a second. So now I've recorded that. Now what I need to know is what is the actual standard deviation? Well, I've already got that. That's this number. And of course, I've already got the standard error. That's this number. So there's my weighted average. In principle, I really should go back, and instead of using this average, I should really use that average in determining this, but it's not that far different. Notice 32.97 versus 32.95. So I'm going to go ahead and fill this in using the same standard error by saying this is 32.950, because that was the next digit, plus or minus 0.019. And since I didn't put the centimeters here, I'm going to put a parentheses and put centimeters there. So that's the two types of results I could actually get. Okay, I'm going to go ahead and save this file. Okay, now I got that. I'm going to kill that right quick. So now we actually have our two different possibilities. If I actually use the 10 separate experiments, then I would have been able to weight the averages or weight their best values and get a best estimate of the weighted average by doing what I just did. But in both cases, the standard error is still just the deviation squared, summed up and then divided by n times n minus 1, and then taking the square root of it, which gives me 0.019. Since that 0.019 was larger than the instrumental uncertainty, I can use that 0.019. If I had come up with 0.008 or even 0.004, I would have had to call it 0.01. Does that make sense to everyone? All right, so that's the mathematical gory details. The only thing I have left to show you on that is there also exists a handy number, a handy value, if you will, and it's called the fractional error. Okay, so that fractional error, I'm going to give you that now. It's just useful in calculations. We usually don't state it by itself, but sometimes we do, just to give us an idea of how good we're doing. But fractional error it has a neat symbol. It's sigma x over x. So the fractional error in x would be sigma x over x. But it's neat because that's the symbol, but the formula is just sigma x over the best estimate of x. So that'll come in handy. So I wanted to introduce that to you. And notice we usually don't even do a percent. Like this would be 0.01 divided by 32.95, say. That's a typical result. You just leave it as whatever that division gave you. You could make it into a percent if you wanted, and that give you an idea how good your experiment was. But other than that, it's not that helpful. So what I'm going to do now is I'm going to share the screen with the actual document you guys are working on. And then I'll show you a couple simple examples so you can get the stuff done. So here's the actual document you're going to be working on. Basically, this is me doing the same thing I just did for those 10 pieces of data, only in this case, I used 6 of them. Okay, so it's all in written form. I talk about the standard deviation. I talk about the percentages, the 68.1, the 95.4, the 99.8. And then I talk about the standard deviation of the mean, which we call the standard error. And I show you how to work out all that. And then I tell you things about using meter sticks and tell the difference and all that stuff. Then I give you these rules, which I've also actually stated already in the video, but when several measurements are made of a single quantity, the average or weighted average is the best estimate of the value. So that's the thing that comes after the equal sign. If you're going to claim that volume equals something, the best estimate is what you put there. Rule 2, the larger of the instrumental error or the standard error are to be used as the uncertainty. So that's what's coming after the plus or minus, in other words. Rule 3, the uncertainty of a given measurement should almost always be recorded with only one significant figure, because if we don't know the leftmost leading digit, we certainly do not know the digits to its right are, what the digits to its right are. The only time you may wish to use 2 sig figs is when the leading digit is 1 and the second digit is like 4 or 5 or larger. Okay, I'm not going to take off for you not doing that, and I'm not going to take off for you doing that. I'm just saying that is a common practice, so it's okay if you do that. I usually just leave it as 1 digit anyways. And if it's a 4, I'm going to call it 1. And if it's a 5, I'm going to call it 0.02, right? Rule 4, your measurement's best estimate should be rounded off to the same digit as the last digit of your uncertainty. So if you use 2 digits, you're going to round it off to that place. If you use 1 digit, you're going to round it off to that place. And then finally, when you're using uncertain measurements to compute something else, you must use the best estimate for the values of the measurements, and error propagation formulas should be used to determine the uncertainty of the calculated quantity and to learn where to round off the calculated quantity using rules 3 and 4 above. Okay, so I basically just told you everything. There's your formula for standard deviation. This is an example table like the one I just did, only the paragraph below tells you how to use it, which I just did, so you don't have to go back over that again. I want you to turn in the whole lab, but you don't have to fill in anything until you get down here to number 1. Here's the standard error formula. Here's the fractional error formula. And now I'm going to give you the propagation of error formulas. Okay. So it turns out, let's say you have, I'm going to, now that I've got these formulas, I'm going to give them to you. I'm going to stop sharing for a second. And let's say we have X is equal to 35, or what was it, 32.9 something? Oh yeah, 32 point, I'm gonna say 32.95. I'm gonna say 32.95 plus or minus 0.02 centimeters is what we just got. Using, in other words, I'm ignoring that 2-digit rule and the digit here was a 1, okay? So let's say that f of x is really just the process of you converting this to meters, because you're going to use it later to find the cubic meters of something. Well, then what you're going to do is you're going to take x, which is 32.95, and you're going to multiply it by 100 centimeters in the bottom by 1 meter in the top, and you're going to get 0.3295 meters. Okay. Well, if you have in general a single variable function f of x, then what I would say, if this is your x value, which we name x bar, and then this distance from here to here is sigma x, and your function did something like this, then you can see your f of x bar would be right here, but you might expect your f of x bar plus sigma x to be over here, okay? And you can probably see that sigma f, this distance right here, is equal to the derivative of f of x with respect to x, absolute value, because we're always going to treat it as positive, times the uncertainty in x. So that's one of our formulas. When you have a single variable, you take the derivative of that function and multiply it by the uncertainty in that variable, and that'll give it to you. So in our case, the derivative of f of x is equal to 1 meter over 100 centimeters. So the uncertainty in f will equal the absolute value of 1 meter over 100 centimeters times 0.02 centimeters, which equals 0.0002 meters. So I would report f as 32 or 0.3295. Let me give it a little bit more space since I was writing that so small. I would report f as 0.3295 meters plus or minus 0.0002 meters. Notice those digits still line up. So that's one of your formulas, but that's the simplest scenario. The formulas can be, for instance, you might have f of x, y, z, and any other number of variables, okay? If that's the case, then the uncertainty in F, the generalization of this is in fact the square root of the partial derivative of F with respect to X squared times the uncertainty in X squared plus the partial derivative of F with respect to Y squared times sigma Y squared plus the partial derivative of F with respect to Z squared, sigma Z squared, plus dot, dot, dot for however many variables you have. That's the general formula for error propagation. So for instance, let's say P of XY. This is a perimeter formula. So P of XY is equal to 2X plus 2Y. Okay. And of course, X is given to be X bar plus or minus sigma X, and Y is given to be Y bar plus or minus sigma Y. So the uncertainty in P is going to be the square root of the partial of P with respect to X. Well, what's the partial of P with respect to X? If I look at this, the way you do a partial is you treat all the other variables as if they're constants. So this is like 2x plus 2 times 3. The derivative of 2x plus 2 times 3 is just 2 because of that 2, not because of that one, right? And the partial of P with respect to Y is going to be 2 times 3 plus 2 times Y. So this is going to give you nothing, but this one's going to give you 2 as well. So I'm going to say it's just 2. Okay, so I'm going to say 2 squared sigma X squared, that's stealing that number right there, plus 2 squared sigma Y squared, stealing that number right there. So the uncertainty, in fact, would be 4 sigma X squared plus 4 sigma Y squared. That's easy, right? That literally means you're going to take 4 and you're going to multiply it by this number right here squared. And then you're going to take 4 and multiply it by this number right here squared. You're going to add those two, take the square root, and then you can report P is equal to X bar, Y bar, plus or minus the sigma P you just calculated. Does that make sense? It would, it probably would look a little better if I said something like, let's say this is 4.89 plus or minus 0.03, and this would be 6.21 plus or minus 0.07 centimeters, put parentheses around everything like that. So in this case, you get P is equal to 4.81 centimeters times 6.21 centimeters. This is my best estimate of P. And when I do that, I'm going to get 4.81 times 6.21, and I get 29.87. But we still don't know where to round this yet. So I'm going to write all the digits I got, 29.87 square centimeters. Now, according to the formula I just derived, sigma P is supposed to equal 4 times, now sigma X was 0.03 centimeters squared, plus 4 times 0.07 centimeters squared, square root. So 0.03 squared is 0.0009 times 4 is 0.0 0.036 plus 0.07 squared is 0.00049 or 0049, and then times 4 is 0.0196. And now I'll take the square root of all that. So I'll say plus so I added them, which gave me 0.0232. And now I take the square root of that and I get 0.152. And that should be in units of centimeters. Okay. So what I'm going to report P as is I'm going to say P is equal to, I'm going to use the 2-digit rule since that's a 1.5, and I'm going to say 29.87 plus or minus 0.15 centimeters squared in parentheses. Does that make sense to everyone? Any questions on that? All right, so let me show you another example and then we'll call it. So this other example is going to be V of X, Y, Z is equal to X times Y times Z. And let's use those X's and sigma X's up there. And I'll say Z is equal to 3.19 centimeters plus or minus 0.01 centimeters. Okay. So I can see the partial of V with respect to X. That's like X times 2 times 3. Well, the derivative of X times any number is just that number. So it's 2 times 3, which in this case is YZ. The partial of V with respect to Y, can y'all figure out what that one is?
It would be XZ.
Exactly. And finally, the partial of V with respect to Z. Should be XY. Okay. So I think this is enough examples for you to understand how to do partial derivatives, because you're not supposed to necessarily know how to do that yet, and that's fine. So now I'm going to use my formula and say sigma V is equal to the partial of V with respect to X, which is YZ. Now that's interpreted as Y bar Z bar. So I'm going to write Y bar Z bar squared, because I got to square the derivative. Remember, the derivative is actually squared, times sigma X squared plus X bar squared Z bar squared times sigma Y squared plus, this was an X2, right? Yeah, that was an X, plus X bar squared Y bar squared sigma Z squared. Now that is the right formula and it'll work, but you've got to put in 3.19 here, or 3.19 here. You got to put in 4.81 here, or 4.81 here, and you got to put in a 6.21 here and a 6.21 here, and then you got to put in a 0.03, a 0.07, and a 0.01 and all that. And it's just ugly, right? Worse, oh, it's ugly. So what I'm going to do is I'm going to calculate sigma V over V, the fractional error in V. Now the fractional error in V is just the uncertainty in V, which I just calculated, divided by X bar, Y bar, Z bar. And of course, if I want that inside the square root, I'm going to have to square all these. So I'm going to do this. I'm going to write a big square root, and I'm going to write Y bar squared, Z bar squared, sigma x squared plus x bar squared, z bar squared, sigma y squared plus x bar squared, y bar squared, sigma z squared. And then inside of all this junk, I'm going to have to take x bar and square it, y bar and square it, and z bar and square it. Well, that's nice because notice in this first term, I've got sigma x and everything but x cancels out. So the x stays in the bottom. So I get the square root sigma x over x squared. Same thing happens with the middle term. So I get sigma y over y squared, remembering that's technically x bar and that's technically y bar. And finally, sigma z over z, again, that being z bar squared. So now I can calculate this really easily. I can just take this sigma x, which is 0.03, over the actual x, which was 4.81. And I'm going to square that, plus 0.07 over 6.21. I'm going to square that. Notice the units are canceling out. That's why I'm not taking the time to write them. And then I'm going to take plus 0.01 over 3.19 and square that. And that'll have no units. So when I do this, I'm going to take 0.03 divided by 4.81. And I'm going to square that. And now I'm going to say plus parentheses 0.07 divided by 6.21. I'm going to square that. And I'm going to say plus parentheses 0.01 divided by 3.19. I'm going to square that. And I'm going to get square root of 0.000175788. So now I'm going to take the square root of that number. Y'all can see the number there. It was 10 to the negative 6. So I'm going to take the square root of that number by hitting square root and then hitting answer. And I get 0.0133 is my fractional error. I'm carrying a couple extra digits there. Okay. In fact, I could say 0.01326 if I wanted to. That might even be nicer. Okay. So what that means is my sigma v is my fractional error times my actual v. Well, my actual v is equal to x bar, y bar, z bar, which I'm going to write now, calculate. So 4.81, well, 4.81 times 6.21 times 3.19 gives me 95.2856. And that's centimeters cubed. Okay, so I'm going to write this answer over here and underline it so we don't lose it. And that's centimeters cubed. Okay, so now I need to take this 0.01326, which has no units, and multiply it by 95.2856 cubic centimeters. So I did that answer times 0.01326. You can't see that there. I did that answer times 0.01326, and that should give me 1.263 cubic centimeters as my uncertainty in V. Now, clearly, I don't know the volume to within a whole number because that didn't come up with any exponents on it. So I actually have to report the V, the volume of this thing is going to be reported as V is equal to, using just one digit, I'm going to say it's 95 cubic centimeters plus or minus 1 cubic centimeter. So that was really horrible, but that's mainly because I made the error so large. The 0.07, the 0.03 were really large, and that 0.01 wasn't going to save it. So now you've seen how to manipulate the formula to get formulas you want. And in fact, what you'll find out is that whenever you have a bunch of products, X times Y times Z or whatever, you're just going to have the fractional error is equal to the square root of the sum of the squares of the fractional error. And whenever you have a sum like X plus Y plus Z, it's just going to be the uncertainty squared is equal, or the uncertainty is equal to the square root of the sum of the squares of the uncertainty. So back to that document, and then I'll let you go. So there's a typo right here. This is supposed to be sigma A over A, okay? And this is not supposed to be there at all, that Z, because there's no Z over here, right? So everybody make note of that error, but this document's going to be on there. And what you're going to do is you can use these formulas, but you can see this is all more explanation stuff. But once you get to here, this is the part you got to do. So I want you to show that for f of x equals x plus y, that you just get this. And for f of x equals x minus y, you just get this. And for f of x equals y minus x, you just get this. And for f of x, y equals f of x, y, z, I should say. F of x, y, z equals x, y, z. I want you to show that you just got that. And for f of x, y equals x over y, I want to show you to show that you just get that. And for y over x, I want to show that you just got that. Then this is where I want you to actually fill in that table by hand. You don't have to show hand calculations, but you have to show all these filled in. And then you can use your calculators to average them or to take the sum and average them. But I want all these spaces filled in. And then I ask you questions down here. And then I tell you to use one or the other. But if you use both, I will give you extra credit. You just got to turn in at least a photograph of your output of your calculator. And you can put them right in here. So when you do this, I would recommend you do this derivation by hand on a piece of paper, then take a nice clear photograph of it, click on the end of this line, hit return, and then insert the picture between there and make it big enough where I can read it. Then do the same thing for this one, then do the same thing for this one. Does everybody understand that?
So you want us to like copy and paste a picture of our written work into the digital document?
Yeah, like you do with the labs with sample calculations. You could typeset it, but you know, it's really a pain in the butt to typeset. And I would, if you're going to skip a lot of steps to save time on typesetting, I don't want to see the typesetting. Okay, I need to see the steps. And that's it. Okay, like I said, you'll get 50 points for staying here all this time. There's, you know, a couple questions here. I'm actually going to get you to do something where you're using X, Y, and Z here and the errors, and you're going to give me the uncertainty in the volume, the best estimate of the volume and stuff like that. And I say, do not use a weighted average. I'm not requiring you to do that. If you want to get extra credit, I could like you to do that, but it's really not that necessary. Okay. And you folks are free to go. That's it. I'm going to, if this isn't posted there right now, it's going to be posted in a few minutes. So just wait up and it'll be there and I'll have a place for you to turn it in. And
the same with the video, with what we're watching now?
Yeah, I'm going to put this video up. It'll probably take an hour before this one gets up.
Okay, thank you.
But it'll be up. Okay.
Thank you.
You're welcome. Thank you, guys.
Have an excellent day, Professor.
You too. If anybody has any questions, feel free to ask. It's okay if I blew you away with this. That's pretty normal.
Professor?
Yes.
So you said the video might not be up for like another hour?
Yes, sir.
Okay.
There's a video on my YouTube channel already where I did the same thing, but it's from another class. So you can still check that out if you'd like.
Okay.
Professor, I wanted to check back up with you about the test 2.
Yes, I'm gonna let you do it. I just decided I'm gonna take 10 points off for being late. And I just, let's not do that anymore. It won't be a problem, but I did have 2 people, so they're all getting 10 points off.
Thank you.
No problem. But you still get your best attempt. So, try to get 100, so you'll still get a 90.
When will you reset the date that it's due?
What's that, William?
When are you going to reset the date that it's due?
I'll do it right after this.
Okay.
Professor,
Yes.
I was also wondering if you had gotten a chance to look at my labs 3 and 4.
No, I'm still working on lab 2.
Okay.
Was there something specific you had to ask me? I know I've talked to you about it before, but it's probably slipped my mind.
Oh no, I was just asking if you had a chance to look at my labs 3 and 4 yet.
Yeah, if you read what I told you was done wrong in the second lab, chances are the rest of your grades will be 95, 100, maybe a 90 if you forget something. But that's about it. So yeah, I'll get to it soon. I'm really behind, but I'll catch up. Don't worry.
Okay, thank you.
No problem.
Have a nice weekend.
You too. Austin,
Thank you.
Eliza, Patrick.
There we go. Can you hear me?
Yes, I can. What's up, Austin?
Can I use Wabbit EMU? It's a Texas Instruments emulator.
Yeah,
or,
that's fine.
Okay. And then also I turned my last lab in at
Mhm.
like 1:40 today, and it said that it was late. It was set for 12:55.
That's an error. Yeah, it should have been set to 155. My fault.
Okay, cool.
I'll correct that.
All right, thank you.
All right, see ya. All right. Is anybody else here, Patrick or Eliza?
I just had a question about the midterm. I know it's too early, but since I have a vacation coming up, I wanted to talk to you about it.
Okay. Yeah,
Um,
it's supposed to be, I think it's like the 3rd week of October, if I remember correctly. I don't have the syllabus in front of me, but that's what I'm shooting for. Are you going to be gone at that time?
yes, I have a vacation coming up from the 13th to the 23rd.
Yeah, that sounds like you might miss it, but I can set it up where you can take it immediately after, or I'll try to set it up where you can take it before, whichever you would prefer.
Probably before, so I don't have to study during the
Yeah, that's what I would
vacation.
think. All right, I'll try to set up that earlier for you, and just keep on me if you don't see any progress on that next week. Remind me again, but I'll do it for you. Okay.
Okay, thank you so much.
All right. See you, Eliza.
All right, bye.
Patrick, chat something if you need me. Otherwise, I'm gonna go ahead and sign out because I think you might be logged out by accident. All right. See you, folks. Have a good day.